Thanks for coming. My name is Oleg Borisov. I'm an assistant professor of the Faculty of Control Systems and Robotics at my university. It is a great pleasure to me to open this St. Petersburg Summer School on Nonlinear Adaptive Control. This is going to be an exceptional event, at least from several perspectives. First of all, during these 3 days, we will have opportunity to listen, to watch lectures given by leading researchers, about professors in control community. You all know their names from the program: Alessandro Astolfi, Romeo Ortega, Alberto Isidori, Vadim Utkin, Arjan van der Skaft, and Stefano Strumigioli. We really appreciate that they accepted the invitations and they becoming a part of this exceptional event. Thank you for Romeo Ortega for organizing all these things. Another awesome thing that this school is absolutely free for participation that makes this event exceptional. So in a couple of words before we start about the program, all the lectures are supposed to be 3 hours, and dear lecturers, of course you may make breaks within these lectures whenever you like to feel comfortable. Also, by the end of each day, we will have a special time which can be used to friendly conversation with lecturers, with coffee, with cookies. We can discuss various things, not only scientific things, but also maybe personal something. And so all of you will have opportunity to talk to leading researchers in the control community. So I hope you will enjoy this, this summer school. And now I'm going to introduce our first professor, Professor Astolfi from Imperial College of London. He's going to talk about modern techniques in nonlinear control and model reduction, right? So I give the floor to him.
All right. Thank you very much.
Yeah.
Hi, good morning, everyone. Before I even start, I would like to thank Oleg and Anton for the invitation, Romeo for insisting beyond reason that I should be here. So it is clearly a great pleasure, and yeah, and an honor. It's a bit intimidating as a room, but it's a very nice room. Right, so the topic of my lectures, and as you see, I will be only using the whiteboard, because if I use the slides, it's going to be far too quick, and that's not the purpose of this, is to discuss model reduction for nonlinear systems. And model reduction is clearly a vast area of research, and it is fairly well understood for linear systems, but unfortunately, the linear way of thinking most of the time is misleading. So the rules of the game, in a certain sense, are to try to discuss initially some issues in model reduction for linear systems without using linearity at all. And once we manage to achieve this, then we can easily extend all of this to nonlinear systems. So before we start on the technical side, I will very briefly discuss what is, in a very abstract sense, the problem of model reduction for general system, regardless of how these are described. And then I will sort of focus on some of the technical objects that we will have to use in the model reduction. Now, model reduction is vastly used these days because even if simulation tools are fairly advanced and fairly quick. I mean, if you, for example, would like to model the thermal properties of an integrated circuit with millions of components, and even if the integrated circuit is very small, it will have kilometers of wires. I mean, these are very tiny wires. Then it is extremely difficult to write a model. So you can write a model using essentially the equation of the system that describes the interaction of all the various components of the system, and then you end up with models with millions of equations. If then you would like to do a simulation of these in order to understand whether, for for example, the layout of the circuit makes sense, then it will take several days to run this simulation. And then after several days, chances are that you will have to redesign the topology of the circuit in order to try to understand whether this is the right topology, for example, in terms of energy dissipation and heat generation for your integrated circuit. Another typical application of model reduction is on the prediction of the surge wave in the North Sea, and this is particularly interesting in the Netherlands, where they need to open or close Rotterdam Harbor as a function of the tidal wave coming from the North Sea. And then to do this, you need to, in a certain sense, integrate the shallow water equation for the North Sea, and this is a very complicated numerical problem. So you would like to do this online because you want to decide now whether you're going to open or close the dam for Rotterdam Harbor, and you would like to keep them as to keep the dam open as long as possible. So also in this case, you have to have a reduced order model, which means a simulation model which describes essentially the tidal wave in a way that this can be simulated online. So from these two examples, and there are plenty of other examples, you can design reduced model for building if you want to discuss, understand the relationship, the interaction between building and wind, or the effect of earthquakes on buildings. So you can always write, millions of equations describing a system, but then these equations are not very useful in practice because when you try to do simulation, there's numerical problem, there are, memory problem, and most of the time you have a problem with time, the time that it takes to do the simulation. So the underlying principle of model reduction is very simple. So you're given a system, and for the time being, we call this sigma. This is an underlying physical system. As I said, it could be a building, it could be the tidal wave in the North Sea, it could be the equation, the Kirchhoff equation of an integrated circuit. And together with this system, you would like to define a model, right? So in a certain sense, the model should be a simplification of the system in a sense that we would like to discuss. Okay, so you're given a system, and then you're given a model, and the model should represent the system under given operating condition. So the model should describe the system under given condition. So this means that if I want to capture a given condition, I can start considering an input signal acting on the system, and then the same input signal will have to act on the system and will have to act on the model, because the interaction of the model with the external world has to be a physical interaction, pretty much like for this system. And then I need to use a particular output of my system, and then I construct what is essentially the most important ingredient in any model reduction method, which is the so-called error system. So there is an input, there is an output associated to this, a new output associated to the model. While this is a physical output, this is a sort of artificial output because it's sitting into your reduced order model, and then you construct the error system. So what you really would like to have, you would like to have that some norm, and I'm not going to be very precise here, so this could be, for example, an L2 norm of the error has to be upper bound by something, and we're going to be slightly more precise in a minute on what this should be, which is also a function of the norm of the input. As I said, I'm not going to be very precise in terms of the particular norm that I use. It could be an L2 norm, an L infinity norm. It's not really important. This simply is a measure of the size of the error, and this is a measure of the size of the input. So what type of ingredient we would like to add at this point? So the type of ingredients that we need to add at these points are a measure of complexity for the system and the measure of complexity for the model. Now, all of us have done some simulation in MATLAB, and so if you have to define a linear system, you need to enter the matrices A, B, C, and D, which essentially means you need to enter the dimension of the system. So it is quite standard, at least for linear system, to have a notion of complexity of a system associated to the dimension of the state space. Clearly, you may consider number of input and number of output, but chances are that most of the time these are much smaller than the number of the states of the system. So the variable that we have to put into this are essentially the dimension, and I'll call this n, which is the dimension of the state space of the system, and the dimension of the state space of the model, which I call it Ni. And clearly, the model, to be a reduced order model, has to be such that n should be smaller than n, and chances are that I would like this to be much smaller than n, otherwise I won't save a lot of computer power. So if this condition is satisfied, then I say that M is a reduced order model. So this function, which actually quantifies the relationship that I would like to enforce for the error system, has to be a function, at least as a first approximation, of n and the variable n. And what properties do we have of this function? Well, the most important property that we would like to have a sort of consistency of this. Now, clearly in all these analyses, I'm being somewhat non-precise because there are issues, for example, associated with initial conditions, which I'm not considering, and issues about stability of this particular system, which I'm not considering. So this has to be taken in a way that is sort of conceptually right, but it has to be fixed by a certain number of assumptions. So this particular function here, which measures, in a sense, the sort of gain of the error system, have to have the property that the limit for n going to n of this function n of n should be equal to 0. This means that if this model is as complex as the original system, then no matter what is the input signal, then I will have an error signal which is always identical equal to 0. Okay? So this condition, ideally, should be satisfied for all selection of the input signal, right? So I can say that if for all selection of the input signal u of t, the condition norm of E smaller or equal than phi of this function of n and E times the norm of the input u. So if for all selection of the input, this particular condition is satisfied with the additional consistency condition that phi and n is equal to 0, then M is a model of the system sigma. And it is a reduced order model. If I pick n much smaller than n. Right? So I build a reduced order model provided I'm able to satisfy this condition for all selection of the input for some function phi which satisfies this consistency condition, and then if I pick my n to be much smaller than n. Now, unfortunately, this is a very simple objective to satisfy, but as every simple objective in math is almost impossible to satisfy. And then the other observation is that it's true that we have this consistency condition, but in every real system, you end up having n equal to several millions, for example, and your reduced order model may be a few hundred states. So even if this consistency condition is satisfied, you'll be a long way away from n equal to n. Right? So you would like to get a sort of simplified version of this notion, and you would like, for example, to make sure that even if your reduced order model is sufficiently small compared to the original model, then you can still have an error condition like this one. So how do you weaken this condition, which is a sort of ideal requirement on your reduced order model? The simplest possible way to weaken this condition is to get rid of this for all selection of the input signal. Right? So what I would like to have, I would like to restrict myself to particular selection of the input signal, and this makes perfectly sense from an engineering perspective. If we would like to construct the reduced order model of the Russian power grid, chances are that we're interested in a 50 Hz behavior, or we may be interested in a behavior close to 50 Hz, but clearly we're not interested in the behavior in the kilohertz or in the megahertz range, because the power network doesn't operate at that type of frequencies. If we are, again, interested in the tidal wave in the North Sea, we are interested in particular frequencies which are associated to the tidal waves. And these particular frequencies are actually very slow because the tidal wave is once every day. So again, we're not even interested in hertz. We are interested in very low frequency. Chances are that we may be interested almost in the DC behavior of the system. So in order to have a definition of reduced order model that we can actually capture and in a more precise way, and that we can construct this reduced order model in a simple way, we have to get rid of this particular selection here. So what we would like to have, we would like to have a new definition whereby we pick a particular set of input signal. So for a selection of input UDT, the condition norm of E, where again I'm being particularly relaxed in the definition of this norm. It could be an L2 norm and an L infinity norm. The norm of E should be identical equal to 0. Okay? So this means that I can actually be much more clever than what I'm doing here if I restrict my attention to a particular selection of the input signal. And this is something which is typically done, for example, in identification for linear system. So if you have a linear system and you do identification in the frequency domain, chances are that you will excite your linear system with some particular sinusoidal input. You identify a point on the Bode plot, and then you will construct a model which actually interpolates, and this is the right word that has to be used, the frequency response of the system in this particular point on the Bode plot. So for linear systems, one often uses ut equal a sinus of omega t. So which means that you excite your system with a particular selection of the input signal where omega is fixed, and then you're looking at the frequency response of your system and you try to reconstruct a reduced order model such that only one point on the Bode plot of your system is satisfied. But there are other conditions that you may wish to satisfy when you, for example, identify a linear system. If you have, in the single input, single output case, a non-minimum phase 0, this is a very important information that you would like to capture. And so you would like your model to capture the behavior of the system in a particular point in the complex plane. So this means that there is a particular input signal that you should apply to your system and to your model with the property that the response of the error system is actually well defined, and we'll come back to this in a few, in a few minutes, and then it satisfies this condition. Now, clearly, as I said, all these analysis is very high level and is very abstract and relies on the fact that I'm neglecting, for example, initial condition, I'm neglecting transient behavior, and I'm neglecting at all stability properties of this interconnection. So I cannot even define all these objects if trajectories are not well defined. So this means that if I want to be slightly more precise, I will have to and not only restrict myself to particular input signal, but I will have to restrict myself to the so-called steady state error of this interconnected system. So I will have to add here an assumption that this condition has to be satisfied only for the steady state error. And this means that in particular, I will have to make sure that a steady state condition is actually satisfied by this interconnected system. And again, we will define this precisely. Okay, so we have now an idea of why model reduction is useful in terms of reducing the complexity of the representation of a system, because you would like to capture only some particular behavior. And we are also introduced what is the main ingredient of any model reduction technique, which is essentially the so-called error system. If you have done balanced truncation, for example, you define an error system pretty much in this way. However, the properties that you're interested in is not a property in the time domain, although you can give an interpretation in time domain, but you're interested in the Henkel singular values. So you would like to make sure that the Henkel singular values of these two objects are exactly the same up, to the first Henkel singular values. Here we are interested, as the title of this lecture implies, in this idea of model reduction by moment matching, which is somewhat inspired by the idea that I'm trying to do interpolation and trying to do approximation in the frequency domain for linear system, or corresponding to some particular point on the complex plane. If, for example, you would like to capture the behavior that the system has a non-minimum phase zero somewhere. However, all this approach that relies on frequency domain interpretation, although very useful for linear system, is not particularly useful for nonlinear system, because most of these notions are very difficult to, to find or to port into the nonlinear world. So we will have to take a slight detour in order to try to understand how to construct all these for nonlinear systems. All right, so before we do this, I would like now to introduce a few tools that we are actually going to use in order to try to understand exactly what a model reduction process is composed of. So the basic ingredient of any model reduction procedure is the notion of projection. And the notion of projection is, in a certain sense, related to the notion of coordinate transformation, or is very similar to a coordinate transformation. And we will see why it is very similar, because the algebra associated to this is somewhere very similar, but clearly we have to be careful because it's not a coordinate transformation. So let's start with the idea that we have a linear system, and then I would like to perform a projection of the state of the system along a particular subspace. So the whole point is that I'm given a linear system, x dot equal ax plus bu, y equals c of x, and all what I'm saying can be easily described for multiple input, multiple output systems. So the number of input and output is not so important. What we really need to keep track of is the dimension of the system, so that x of t is actually a vector in an n-dimensional space. The matrix D, as in most system theoretic sort of arguments or discussion, doesn't really play any significant role. Okay, so I want to define now two matrices, which are projection metrics. So the first one is a matrix T, and I call this matrix T because this matrix is going to be a tall matrix. So this matrix is going to have as many rows as the dimension of the state of the system, and as many columns as the dimension of my reduced order model. So I would like to sort of construct a model which is of dimension n. N could be smaller or much smaller than n. And so to this end, I construct in some way a matrix T. And then I define a second matrix, W transpose. And this W, again, the name is such that this matrix is a wide matrix. And so it is with this particular form. So it has as many rows as the dimension of the reduced order model, and as many columns as n. Now, the property that I want for this to be a projection is that W transpose T has to be equal to the identity. And I won't keep track of dimension of identities, but clearly in this case, this is an identity of dimension n. Okay, so I've been told that there is only one identity matrix, so I don't put the index there. Right, okay, so what do we do with these two particular matrices? Okay, so the whole idea is to approximate the state x of t using the matrix T times a vector x tilde. Okay, so this vector lives in Rn, and this vector lives in Rn. Okay, and that's exactly how I define this object. Now, clearly, this is not an equality sign. This is an approximation sign, right? But I would pretend, for the time being, that the state x of t can be written in this particular way. So if the state x of t can be written in this particular way, then I could actually define, a differential equation which involves x tilde. And the way I define this differential equation is essentially to differentiate this object, pretending this is an identity. And so I obtain that x dot is equal to t x tilde dot. And then I know that this is equal to AX plus BU. However, since there is an approximation, there will be an additional term rho, which is associated to the fact that actually these two objects are not really the same. So this is like a residual error, which is associated to the fact that I'm pretending that this is an equality sign, but actually is not an equality sign. And then you see that I could start replacing some of the object. So for example, x is equal to tx tilde. And so if I keep only track of the second part of this equation, I have that tx tilde dot is atx tilde plus bu plus rho. And then you see that rho, which actually describes the mismatch between the state x of t and the approximation of this particular state that I'm using, in a certain sense, has to be removed. And the way in which I could remove this quantity is essentially selecting the matrix Wt. So if I pick Wt such that W transpose rho is equal to 0, in addition to the requirement that W transpose T is equal to the identity, and this requirement actually can be waived, and we will see in a minute how this can be waived. Okay, so this is actually not required, but it makes our life much simpler at this stage, so we'll get rid of this in a minute. So if I pick Wt such that that condition is satisfied, then I can left multiply this equation by W transpose, and so I will have that W transpose T times x tilde dot is equal W transpose AT x tilde plus W transpose BU, and then the terms W transpose rho goes to 0. This is exactly how I constructed my matrix W. And so I now have a differential equation in the variable x tilde. So I can write that x tilde dot, because this quantity is actually an identity matrix, at least as a simplifying assumption to begin with, I have that x tilde dot is W transpose AT x tilde plus W transpose BU. And then the output equation, which is most of the time not particularly interesting, is simply y equal ct x tilde, which is simply obtained replacing this approximation of the state x of t with my ansatz for this particular approximation. Now, you see immediately that what I said at the very beginning, that projection plays a similar role to actually what is the notion of coordinate transformation, although you have to be very precise, because if now T becomes a square matrix and then W is essentially the inverse of T, then here you have precisely the representation of the system in a new set of coordinates. Now, this is now a reduced order system. You've performed a projection, so you don't really have a matrix T, which is a square matrix, but this is a tall matrix, and then you essentially apply the trick of projecting everything using W transpose and reducing the dimension of the state space. But the way the matrix A, for example, transforms is exactly the same. So this is a way in which I typically remember this expression. Now, you also see that this requirement, that W transpose T is equal to the identity, can be easily removed, because if instead of being the identity, so if this matrix is actually different from the identity, the only thing that I get is that I need to change this equation, and then this matrix has to be invertible, and I left multiply by the inverse of this, and then I have W transpose T minus 1 W transpose AT x tilde plus W transpose T minus 1 W transpose BU. And the output equation is left unchanged. So the fact that this W transpose T is different from the identity is simply making the analysis slightly more complicated, but actually is, slightly more complicated, and the formula a bit more awkward, but actually is not really a very restrictive either assumption, or we can get rid of this in a very simple way. Now, there is a very natural selection for W if we simply assume that we don't require this to be the identity matrix, but it has to be invertible, which is to pick W equal to T. So if you pick W equal to T, and don't forget that W transpose is W has the same dimension as T, then you end up with what is called the Petrov-Galerkin projection. Right. Now, model reduction is always related to projection. I mean, there is every method that you can think of in model reduction, even Henkel norm approximation that we have not discussed, but we simply mentioned, can always be interpreted in terms of projection. Depending on the particular way in which you pick this particular object, in which you perform this projection, you have some particular properties. For example, if I pick W equal to T, you have something which is very popular in model reduction for nonlinear system, which is called this Petrov-Galerkin projection. Now, there is, as a side comment, there is a technique which is called proper orthogonal decomposition. And the technique of proper orthogonal decomposition is based on this idea of projection, and in particular is based on a particular way in which, so this is proper orthogonal decomposition, in which this projector D is selected. And this is actually selected considering a snapshot of the states at particular time. So I pick ni times, T1 up to Tni, and then I pick snapshot of the state vector, and then I construct this matrix T in this particular way. The matrix W can be constructed in somewhat similar ways, and then I obtain what is called the proper orthogonal decomposition. Now, you could immediately argue that doing something like this is completely silly, because if I, for example, would like to build a reduced order model of the tidal wave in the North Sea, I don't really have a measurement of the state, let alone that the state is actually an infinite dimensional state. However, what you could do, you could build a very sophisticated simulation models, which essentially is integrated in this particular example, the shallow water equation, or you could, write Kirchhoff equation for an integrated circuit with, several millions of components, which is, after all, what is one of the integrated circuits in every computer. So you write a very precise simulation model, you run the simulation model, you collect snapshot of these simulation models, and then you construct a reduced order model out of this synthetic data, right? These don't have to be measurement of the actual state of the system, but can be measurement of synthetic data. Now, all this process that I've done can actually be, for linear system, can actually be repeated also for nonlinear systems. Now, I'm not really going to discuss, because of reason of time, the geometry of this particular projection. In the literature, sometimes these are called oblique projections, because the subspace that you define through T and the subspace that you define through W, they're actually not orthogonal most of the time. And if they're not orthogonal, the projection is not a standard projection like the one that we typically imagine, which is, you have a plane and then you have an orthogonal direction to the plane, and then you perform projections of points outside the plane along this orthogonal projection. If these two subspaces are not orthogonal, then you have something which is called an oblique projection, which means you have a plane and then you have a vector which is not orthogonal to the plane, and then you perform your projection along this vector, which is not orthogonal to the plane, on the particular plane. Right? So there is nothing particularly deep with this idea of oblique projection, but if you read the literature on model reduction, it comes very often, and the reason why it comes very often is that these objects, these projectors, are actually not orthogonal. They don't define orthogonal subspaces, and this means that there is this particular geometry. But, it's just a name. There's nothing particularly deep in all of this. Now, if we want to repeat all of this for nonlinear system, we can actually do this in a very simple way. Probably simpler than using this pen, all right? Okay. So, if I have now a nonlinear system, which I can write as x dot equal f of x and t, and the reason why I don't write the input u is that I will regard u as a function of time, and actually that's why I put a t there. So this is still a control system with input and output. However, I don't want to write any specific form for this. And I have an output function which is y equal h of x. So pretty much like I've done for linear system, I perform an approximation of the state pretending that x of t has to be a good approximation, should be described as t of x tilde of t. Now, for linear system, it may make sense to assume that the state of the system evolves in a subspace, right? So this approximation may somewhat make sense. For a nonlinear system, this is a bit far-fetched because you may think of manifold where this linear the trajectory of the system are actually living, but it is actually a big assumption to assume that the state of the system actually lives in a subspace. But for the time being, let's pretend I'm performing projection along subspaces, so I keep on having a sort of linear way of thinking. So we repeat exactly the calculation that we have done this. So this matrix T is always our tall matrix, n times n. I define a W transpose, which is a wide matrix, n times n, and then I differentiate x dot. So x dot is t x tilde dot, and this is equal to f of x and t, plus some error that I've committed with this approximation that again I called rho. So if now I assume that W transpose rho is equal to 0, and then that W transpose t is equal to the identity, and as we said before, this is only for our convenience, because otherwise all these inversions are going to get slightly more complicated, then you see that I have that tx dot tilde is actually f of x, which I write as t x tilde times t plus rho, and then I multiply everything by W transpose, and so W transpose t is the identity, and I end up with x tilde dot equal W transpose f tx tilde t, and then W transpose rho is equal to 0. And the output equation, y is equal to h t of x tilde. So you see that I can extend this idea of projection to linear system, from linear system to nonlinear system in a very simple way. And essentially use exactly the same ingredients. There is this approximation idea or assumption, which, it may be realistic for linear system, is somewhat unrealistic for nonlinear system, and then there is this notion of projection along, using W transpose to remove this additional term, which is, in a certain sense, a quantification of the approximation of the error between these two objects. Okay, so in a certain sense, you could say, well, fair enough. So a very simple way of constructing the reduced order model for linear or nonlinear system would be to have either measurement of the states of your original system or a very precise simulators. Then you capture a certain number of snapshots. You construct this matrix T. You construct W in order to satisfy this particular condition, for example, and in a certain sense you hope that this condition is satisfied, and then you rewrite your reduced order model in this particular way. Okay, so this is something that we can implement in a few lines of code, but then, as control theorists and engineers, we would like to understand whether this process actually makes any particular sense. So, in particular, we would like to understand what are the properties of this reduced order model and whether we can, in some sense, manipulate these properties in order to capture the behavior of the original system. We should never forget that this reduced order model has to be a representation of the original system under some particular operating condition. Okay, so the first observation is that I'm given this particular system, and then I would like to perform simulation on this. So if I'm given initial condition on this system, I should be able to get initial condition also on this particular system. So I have an x at time 0, and then here I have an x tilde at time 0. Now, how do I construct an x tilde at time 0? Well, in a certain sense, I need to be able to invert this expression, right? And since t is not a coordinate transformation, I cannot really perform an inversion, but I can actually use the property of W to say that x tilde has to be equal to W transpose times x0, okay? So at least if I want to perform a simulation of the reduced order model starting from one particular initial condition, don't forget that the input to the two systems have to be exactly the same. pretty much like in the construction of the error system that we had at the very beginning. Then we can, sorry, there is an equal here. Then we can construct the initial condition in this particular way. So let's try to understand geometrically what we're actually doing in this particular scenario and what are the properties that we gain or we lose. So I am given my plane T, subspace T, which is in a certain sense X tilde that lives over there, so it's the image of T, right? Okay, so then I'm giving an initial condition, which is x at time 0, and then the trajectory x of t doesn't have to live on this particular subspace. I mean, my assumption is that it is a good approximation, but it doesn't have to live there. So for example, this is my particular trajectory. It will intersect this at some point, and then we'll come back and we'll continue in this way. Right, then, performing this particular projection, I now construct an initial condition which lives on the plane, right? So this is now x0 tilde, which lives on the plane. However, on this particular image of T, on this subspace, I have actually two trajectories that I have to consider. Why do I have two trajectories that I have to consider? The first trajectory is actually the trajectory of the reduced order system. So I can integrate this, and then I obtain a trajectory which by construction lives on that plane. So if we write this trajectory in black, then this will be a trajectory that lives on the plane. And then I have another trajectory. The other trajectory that I have is nothing else than the projection of the real trajectory of the system on this particular subspace, right? Don't forget that this is an approximation. So this trajectory is going to be different by the trajectory that I actually obtained projecting x of t on this particular plane. So if I perform this projection and if I use a red pen for this particular projection, I have another trajectory. So this is x of t projected on t, right? Okay, so there is an error between these two, and the error is associated to the fact that the initial trajectory doesn't live on this particular plane. And actually, I can construct this error as the sum of two particular errors. I have an in-plane error, which is this one, and I have an error which is orthogonal to this plane, right? So I have sort of an E perp and an E on the plane. We can call it ET, right? Now, the main problem that I have, so in principle, I could write a differential equation for this, and as I said always to my student when I teach, control people have a strange disease. Whenever they see a signal, they compute the time derivative of that signal. Right? So I can write a differential equation for this particular variable. ET may not be a good name. So let's call it ET in this way. So this is the error on the plane. But actually, without writing even a differential equation of this, the bottom line of this is that I would like, in principle, to have some stability property for this. Clearly, I would like also to have stability properties for this particular error, because I would like to be as close as possible to this approximating plane, so my trajectory should live in this subspace, but this is something upon which I have very little control. If my projection has been selected in a good way, and the idea of proper orthogonal decomposition is precisely to pick this in this good way, because you start with snapshot on the state space, and so you believe that you are close to the subspace. However, for this one, it's very difficult to enforce any properties. So the main problem, so that we have, if we use projection, so the main issue with projection-based model reduction is that there are no, and I can write in brackets, stability guarantee on the ET system. Now, I always hate when people talk about stability of systems, right? So you talk about stability of equilibrium point or stability of motions. However, so that's why I put these brackets, sorry, this quotation sign there. So this means that I would like to have a guarantee that the error system, so ET dot, so this is described in some particular way. This error system has an equilibrium for ET equal to 0. And ideally, I would like to make sure that this is a stable equilibrium. Because if you remember the construction that we have at the very beginning, where we have our system and the model, and we constructed the error system, in a certain sense, the error system is exactly described by these two particular coordinates, one which is an in-plane coordinate and one which is an orthogonal coordinate. And then I would like to guarantee that, for example, if the original system has some stability properties, these properties are inherited by the system that I've reduced. And even if there are no stability properties of the original system, I would like to make sure that at least I'm close when I perform this projection to the behavior of the system on this particular plane. Right. So all of this is to essentially introduce one of the main ingredients in model reduction, which is this ingredient of projection. And believe it or not, any model reduction technique, even if it's sort of in a back-ended way, is always using a projection. So you can always reinterpret any model reduction method using a sort of projection algorithm. All the differences are in the way in which you select the particular projection. This means that if we are then interested in matching, as we said at the very beginning, behavior of the system, in case of linear system on the j omega axis, or we would like to capture the fact that the system has a non-minimum phase 0, we would like to capture the DC gain of a particular system, then we have to do projection in a particular way. This particular way is called Krylov projections. Sorry, Krylov? Yeah, I think so. It's quite interesting because Krylov was a Russian engineer and he was interested in stability properties of sheep. So his original paper on Krylov projection has nothing to do with projection and model reduction, but he was simply interested in properties of eigenvalues of linearized model of large vessels. But it's a very interesting paper. Not that I've read the Russian version of the paper. Right, okay, so. Okay, so if I want to define Krylov projection, now we know exactly what are the main ingredients. So we have to start for a linear system, x dot equal ax plus bu, y equals c of x, and I would like to associate to these linear systems the transfer function ws, which is c as identity minus a times b. I assume that this is a minimal system, so since when you do model reduction, you're interested in input-output properties, you can always get rid of non-minimum parts of your system. This is very easy to do for linear system. It's going to be slightly more tricky for non-linear system, but assume that the system is minimal. Now, for bookkeeping exercise, and because it's going to be useful later, let's write, for example, what is the derivative with respect to s of this transfer function. And so this actually, without doing the derivative, but if I remember correctly, it has a minus here, and then it's c as identity minus a minus 2 times b, right? And you can actually carry on doing all the derivative of the transfer functions, and then essentially what you have some scalar which is showing up whenever you perform the derivative, and then the second derivative will have s identity minus a minus 3, and so on and so on and so on. Okay, so this is somewhat ununderstandable now why I'm writing this here, but it's useful because we'll see where this is going to go in a few minutes. Okay, so we know that in order to perform projection, we need to construct a particular matrix T. So T and W transpose are projection matrices. Sorry? Oh, yes. Sorry, let's call this G. Correct, sorry, my mistake. Okay, all right, so these are projection matrices, and I construct these projection matrices using what are called Krylov subspaces. So I define the Krylov subspace of dimension Q associated to a pair of matrices Fg as the subspace, which is essentially constructed as the image of G, Fg, Fq minus 1G. So this is a sort of controllability subspace. And then I can actually even construct, so I can actually construct this in, well, okay, so I can actually construct a Krylov subspace associated to the system in two ways. So if I'm going to pick the matrices A and B, I construct this Krylov subspace as a sort of controllability subspace. And if I use the matrices A transpose, C transpose, I have what is called an output Krylov projection space. So I have actually two options. I can construct an input Krylov. And one simple way of constructing an input Krylov is to pick G to be A minus 1B, supposing that this exists, right? So that the matrix A doesn't have any eigenvalue at 0. And then the matrix F is actually equal to A. So if I construct the input Krylov in this way, I have the KQ of F, so A minus 1B, B, is actually composed of A minus 1 B. Sorry. This has to be A minus 1. So A minus 1. This blue pen is not ready. A minus 1B, A minus 2B, and so on, up to I have Q minus 1, but I started at minus 1. Then I have A Q minus Q times B. And then I could construct an output Krylov if I pick the vector G as A minus transpose, C transpose, and the matrix F as A minus transpose. Okay, so if I do this, then I have KQ of A minus transpose, C transpose, C transpose, correct, which is actually the image of A minus transpose C, A minus 2 transpose C transpose, and so on and so on. Okay? Now, since our objective is to essentially do an extension of all of these for nonlinear systems, I mean, I'm reasonably happy up to this point, right? Because I'm actually using objects which I can relate to in a nonlinear setting. I'm not particularly happy with this particular construction because as soon as you start doing a transpose of objects, for linear system it's very easy to do, but for nonlinear system you have absolutely no clue what these are about. Okay, so it turns out that the output Krylov projection in the nonlinear framework is extremely tricky to understand, and the reason is essentially because you don't have to go, you cannot go through the transpose of this object, and so you have to approach the problem in a completely different way. But up to this point, I'm actually, following my initial rule, which is to try to understand everything without exploiting linearity in any particular way. So up to this point, I've actually, satisfied this condition. Okay, so I can actually construct T using the input Krylov subspace and W transpose, or W using the output Krylov projection, and then you can ask yourself, what do we achieve if we pick this particular projection? So I think the simplest possible way to understand this is to do an exercise. So suppose, for example, that I would like to reduce this system to a system of dimension 1. So I want to go from, again, n to n equal to 1. Okay? And so I can actually construct T simply picking the first element in this Krylov projection subspace. So the matrix T is A minus 1B. Right? Okay, so I need now to write the projection. So W transpose T has to be equal to the identity, so I can always find the W transpose which satisfies this condition, provided the system is minimum and A doesn't have an eigenvalue at 0. And then the reduced order model, X tilde dot, is going to be equal to W transpose A T, which is A minus 1 B, times X tilde plus W transpose T BU, and then the output Y of the reduced order model is given by C T, which is A minus 1 B times X tilde. Okay? All right, now, don't forget that W transpose has the property that W transpose T, A minus 1B is equal actually to 1 in this particular case. But we're actually not even going to use this property here. Just let me check that everything is correct. Right. Okay, so here I have a reduced order system which has only one property, which has only one state. What are the properties of this reduced order system? So I would like to write the transfer function G tilde of S, which is the reduced order, the transfer function of the reduced order model. So the transfer function of this is C A minus 1B times S identity minus this big A, W transpose A minus 1B minus 1 times W transpose B. Now, if I now evaluate this transfer function for S equals 0, I obtain that G tilde evaluated at 0 is actually minus CA minus 1B. This minus is out of the bracket. And then don't forget that this is a scalar, so I can put this into the denominator. I have W transpose A minus 1, A minus 1B, W transpose B. And so you see that this W transpose B simplifies with this, no matter what the W is. And I simply have minus C A minus 1B. And this quantity is nothing else than G at 0. So you see that selecting as projection matrix the input projection matrix up to one point, so A minus, up to one vector. So if I pick my T out of this particular vector, and sorry, I apologize, this should be all B's like this, right? Okay, so if I pick just this to construct T, I've actually obtained a reduced order model of dimension 1, and this reduced order model is parameterized in W. You see that W is actually a free parameter in this particular way. No matter what W is, I can actually always satisfy this condition, and the reduced order model is achieving interpolation for S equals 0. So I have the fact that G0 is actually equal to G tilde evaluated at 0. I have interpolated the transfer function of the original system at S equals 0 with a reduced order model of order 1. And actually I have 1 degree of freedom to spare. Now, what can we do with this particular 1 degree of freedom? Now, don't forget that this is a scalar system. So, for example, I could pick W transpose in such a way that this condition is satisfied, right? And possibly I would like to impose a stability condition on this. Right? So I would like to make sure that the unique eigenvalue of this system is on the left part of the complex plane. For example, capturing the behavior of the original system if this is an asymptotically stable system. So you see that in this construction of the Krylov projection, I can actually perform approximation of a linear system at some particular point of the complex plane, and this approximation is actually dictated by the particular selection of the input of the Krylov projection matrix that I've selected. And then, since I've selected only one vector, I've actually achieved interpolation at one point. Now, it is actually a matter of quite some painful linear algebra, but if I construct the T matrices, the T matrix out of this, and if I construct the W matrix out of this, if the system is minimal, then W transpose T is not going to be equal to the identity, but is invertible, then the reduced order model that I can construct has the property that G reduced at 0 is equal to G0. The derivative is equal to, evaluated at 0 is equal to this derivative. And this is up to, if I perform the projection Q times here and Q times there, up to G 2Q minus 1. So this is derivative with respect to S prime, evaluated at 0. And this is G0 2Q minus 1. So I'm actually interpolating the system at 0, the derivative of the transfer function at 0, the second derivative up to the derivative of order 2Q minus 1. So, sorry? These are all G tilde, the first derivative. Yes. And this is the 2Q minus 1 derivative. Thanks, Romeo, for keeping my notation straight. Okay. All right. So you can, in a very simple way, construct an approximation of your system, which is nothing else than sort of an approximation of the Taylor series expansion around 0. Now, if you do this approach, you see that you fix the T, you fix the W, so there's no additional degree of freedom left here, and so you have not any idea whether, for example, the corresponding system is going to be stable, even if the original system is stable, or if the system, you have an initial system which is passive, which chances are this is the case if you have a circuit, and then you would like to have a system which is also passive when you perform model reduction. So it is important to understand, for example, that if you would like to retain particular properties in the reduction process, then you may restrict yourself to doing the projection with the T, and then you leave the W somewhat free in such a way that you can achieve additional properties for your system. Now, if you are interested in matching at points which are different from S equals 0, then it's quite obvious what you should do. Instead of picking the matrix A, then you can A minus 1, then you can pick some S bar identity minus A minus 1, and you use this as the F, and you use this here, and so you construct a different Krylov subspace, and this Krylov subspace will give you interpolation around this particular point in the complex plane. Right? So it's very straightforward to do all of this. From a numerical perspective, this approach is not particularly great, because you see that if you have a system of dimension n, and if n is several millions, you have to perform this inversion. Right? So this is not a great object to do from a numerical perspective, and so there are some particular procedures which allow you to perform Krylov projection without doing all this inversion and without doing all these operations, and these are called the Arnoldi and Langston procedure, which are some particular procedure known in linear algebra to manipulate matrices and vectors. All right, so we have now understood that, hopefully, that the main ingredient for performing model reduction for linear systems, in general for nonlinear systems, are essentially projections. And once you have a projection, you can construct this in several ways. You can easily project, I know that this is technically not precise as a word, your system on a subspace, and then you obtain a system which is a reduced order system, which is an approximation in some sense of your original system. Now, if we go back to what I said at the very beginning, you see that if I perform projection, pretty much like I've done at this stage, which means I'm interpolating at S equals 0, suppose that everything is asymptotically stable, the step response of the original system and of this system will have exactly the same steady state value. So the steady state step response of this system is going to be exactly the same steady state response of this particular system because I've interpolated there. If I interpolate G0 and the derivative at S equals 0 of the transfer function, not only the steady state, but also the response to a ramp input will have exactly the same steady state. Okay, so this means that if we want to expand all of this to nonlinear system, then we need, in a certain sense, to define a certain number of objects, and these objects are somewhat associated with the notion of steady state for nonlinear systems, and also with a new object. So up to now we have, I say that I've been trying to use everything related to linear system without exploiting the linearity properties, but I actually have not been 100% true to my words. And the reason why I've not been 100% true to my words is that I've used the transfer function here. I used the derivative of the transfer function with respect to S, and then I've evaluated this at particular points. So I'm still using some objects which are pretty much only linear, and I have no idea what is the nonlinear equivalent of this object. And then I've performed an operation which is a derivative with respect to S of an object which I cannot define for nonlinear system, evaluated at the point in a complex plane, which is again something that I have no clue whatsoever what is for nonlinear system. So I need to be able to bypass all this procedure, construction of the transfer function, derivative with respect to S of the transfer function, and in some way I need to be able to define this object here. Right? So these objects here are what we call the moment of the system at S equals 0 in this particular instance. So this is the moment of the system at S equals 0. This is the zero order moment. The derivative is going to give you the first order moment, the second derivative is the second order moment, and so on. So in order to extend all of this to general nonlinear system, I need to try to understand what is this projection for nonlinear systems, and I also have to try to understand how I can construct moments for a nonlinear system without exploiting the notion of transfer function. Okay, so this is exactly what we are going to do in a minute. In this particular way, they are, in the case, yes, but if they are evaluated at some point in the complex plane, these are the... No, but not if they are evaluated at some S bar. Okay, yeah, clearly. Then, if you want to do approximation around 0, then it's essentially you're approximating the Markov parameter of your system. So, the short answer is that I've tried and have been unsuccessful. So I don't know. Sorry? Well, it's slightly more complicated. What do they do? The main and this is coming a bit outside all these lectures. The main problem in subspace identification that I cannot relate to for nonlinear system is that they heavily use Cayley-Hamilton theorem, right? I mean, even if it's hidden somewhere, Cayley-Hamilton theorem is in action all the time when you do subspace identification. And since I have no equivalent of Cayley-Hamilton theorem, I can actually construct a certain number of objects which are related to subspace identification, but I cannot really push this to the very end. I mean, probably someone smarter than me can do. Yes. I've tried to do subspace identification for nonlinear system using this sort of ideas and something, clearly related to that, and the stumbling block in all the process is the fact that Cayley-Hamilton is in action there, and I don't have Cayley-Hamilton there. All right, so there is a geometric way to look at the problem, but there are some gaps, so it's not yet complete. Okay, so my objective now is to take a linear system, input u, output y, so x dot equal x plus bu, y equal c of x. And then, okay, so we assume for simplicity, we have an n-dimensional state, and then that this is a single input, single output system. If you want to do model reduction for multiple input, multiple output system, you'll soon find out that actually this is a very weird problem because you're actually doing interpolation of matrices of transfer functions, which means that even if you don't want to do an interpolation at one point, you need actually to approximate m times p transfer functions at this particular point. And so you cannot do this with a transfer function of order 1. And so this means that in a certain sense the problem explodes because of the dimension of the input and the output. And what people do, they typically left multiply and right multiply the matrix of transfer function using what are called tangential direction. There's no tangent really in action, but they're just called in this way in the literature. And then you reduce the multiple input, multiple output model reduction problem to a single input, single output, where essentially you are taking a weighted combination of the input and the output signals. All right, so my problem now is to try to define this object not only at 0, but at any point on the complex plane without going through the transfer function. Okay, so, and the very simple way of doing this is to try to go back to this very small remark that I made a few minutes ago, where I said, well, if I have this system here, and then I construct my reduced order model using only the Krylov subspace, the input Krylov subspace associated with A minus 1, B, B, then the steady state response, assuming this response is well defined, of this system for a step input is exactly the same steady state response of this system for a step input. So I have, in a certain sense, associated this quantity here, which is fairly natural to do so, to the steady state response to a particular input signal. And what is the input signal is obtained observing that if I'm interpolating at s equals 0, I'm actually looking at the step response because the pole 1 over s is associated in the Laplace domain to a step response. So if I now apply a step here, I would like to ask myself, what is the steady state output? And now this is a very simple exercise to do if you have transfer function, and then clearly you need to make the assumption that all the eigenvalue of A are in the left half of the complex plane, and you need, so which means that A doesn't have an eigenvalue at 0, and you can define this. So you can very easily compute the steady state response, but we want to do this without using the transfer function. So the simplest possible way of doing this is to construct a signal generator, which is then attached to the system x dot equal ax plus bu, y equals c of x, and then I would like to look at the steady state response. Now, what is a signal generator which generates a step? Is something which is omega dot equals 0, and the output u is actually equal to omega. Now, clearly, I need to pick an initial condition omega 0, which is associated to the to the sort of value, absolute value of this particular step. It's clearly important that W0 has to be different from 0. Okay? Now, this is actually not the technical assumption that you need to make in order for all of this to make sense. The technical assumption that you have to make is that if you rewrite this signal generator in a more general form, omega dot equal S omega, and then U equal L omega, and then you have an omega 0. So the technical assumption, and I have to admit that I've overlooked this in my original paper on this, is that the tripole L S omega 0, where you regard omega 0 as an input vector, has to be minimal. So you want observability of LS and controllability of S omega 0. And actually, in a nonlinear setting, this is even slightly more complicated because it's not actually a controllability property, but it's called an excitability property. All right, okay, so let's leave this down there for a few minutes. And then what I have now this particular system, which is interconnected with this signal generator, and I would like to compute the steady state response for this. So in order to compute the steady state response for this, I can actually write the interconnected system, omega dot equals 0, x dot equal ax plus bu, which is actually omega, and then the output is actually equal to c of x. Okay? And then I have some particular initial condition, and I would like to construct the steady state output. So how do we do this? Well, this should be fairly classical now, but I can actually construct an error signal, which is x minus pi omega, so where pi is a matrix that I would like to find. And then I write a differential equation, which is E dot equal ax plus b omega, which is x dot. So as I said at the very beginning, as a control theorist, I have this disease that as soon as I define a signal, I compute the time derivative of this. Okay, and then I have times p omega dot. And omega dot is actually equal to 0. But let's write this for the time being, even if this is at 0. And then what happens is that I can now this is b omega. I can now replace x, because I'm now trying to describe my system in the new coordinate, which are omega and e. So I have ax, which is ae, plus a pi omega plus b omega minus pi times 0. And forgive me for keeping this pi times 0, but we'll see immediately why, in a certain sense, it's useful to carry this over. So you see that actually, this is b omega, right? So this, if instead of omega dot equal 0, these were omega dot equal s omega, then I will have an omega term here, right? So if the pi matrix is such that this is equal to 0, then the error signal is going to be described by an autonomous differential equation, which is E dot equal A times E. And since I made the assumption that the eigenvalues of A are in the left half of the complex plane, A is going to go is going to go asymptotically, exponentially to 0. And so I can actually say that E goes exponentially to 0, and the steady state response of the system is actually given by pi omega, right? So I can actually say that x of t is going to give to pi omega t. In this particular case, omega t is a constant, so x of t is going to go to there. So to summarize, we have derive all of these. Under a very simple assumption, which is essentially to be able to interconnect my system under some stability assumption to a signal generator. Y equals C of x. And then I have the Y steady state. So the Y steady state is actually equal to C x steady state, but x steady state is nothing else than pi. So this is C pi, and then omega 0, because omega is actually a constant. All right, so the matrix pi has to satisfy this condition, A pi plus B minus pi times 0 equal to 0. Okay. Now, we can now get rid of this term for a minute. We'll come back to this in a minute. So if A doesn't have an eigenvalue at 0, then I have that pi is actually minus A minus 1b. And then if I write pi here, I have that Y steady state is actually minus C A minus 1b omega 0. And you recognize immediately that this is G0. Right? So I have been able to construct the moment at 0 of the system under a simple stability assumption, provided that I've interconnected this system to exactly the right signal generator without using any linear argument, simply using an invariance condition and the fact that there is always a solution to this equation if A is invertible, and we will see that if there is an additional S there, there's some natural assumption that we need to use in order to define the moment of the system. And then you could say, well, okay, fair enough, this seems to be very convenient, but it's only one moment. Okay, so let's pretend that I would like to compute not only the zero-order moment, but also the first-order moment of the system. So this can be done in a very simple way. I want to compute G0 and G prime evaluated at 0. So G0 is related to the step response. G prime at 0 is related to the response to a ramp input. So this means that S has to be constructed, for example, as 0, 1, 0, 0. And then the matrix L, which is such that, I've got rid of this, but SL has to be observable, can be constructed, for example, in this particular way. Now, we'll come back to this in a few minutes. You don't really have to pick any special form for S of L because these are properties of transfer function or input-output properties. So everything is going to depend on whether you have a change of coordinates. You can always rewrite everything in this way. So it doesn't really matter which particular representation you pick. Okay, now if S is not identical equal to 0, if you repeat all the construction, you are going to end up having an S here, right? So now you need to solve an equation which is A pi plus BL equal pi S, which is a Sylvester equation. Now, if A is asymptotically stable, S has eigenvalues on the j omega axis, so there is no resonance between the set of eigenvalues of A and S, so this equation has a unique solution. And actually, we can compute the solution of this equation in a very simple form. So if I slice pi into 2, pi 1, pi 2, then I can actually write A, pi 1, pi 2, plus BL, with this particular selection of L, I have B0 equal pi times S. And so if I do pi 1, pi 2 times 0, 1, 0, 0, then it's very easy to convince ourselves that if I multiply pi 1, all the elements of pi 1 are multiplied by 0. So I have a 0 matrix here, and then I have pi 1 here. Okay, so this is nothing else than a shift to the right of the pair pi 1, pi 2, and the new entry is actually a 0. So I actually have two equations here, which I could rewrite as A pi 1 plus B equal to 0, and A pi 2 plus 0 equal pi 1. So if I solve for pi 1, I have minus A minus 1B, and if I solve for pi 2, then I have minus A minus 2 times B. So you see now that if I have to compute the Y steady state, so this is going to be C pi. And so C pi 1, C pi 2, and then this is omega t. And what are C pi 1 and C pi 2? They are nothing else than minus C A minus 1B and minus C A minus 2B. Right? So this means that through pi, I've actually been able to construct the moment G0 and G prime evaluated at 0 of the original system, and I've done this solving a Sylvester equation. Right? So clearly, pi is nothing else than the Krylov projection, and the input Krylov projector. And actually, in this particular coordinate, they're exactly the same. I mean, if I've used a different set of coordinates for this one, I mean, I could have picked L to be 1, 1, or, S, 0, 0, 0, 0, 0, 1, 0, for example, then you get something else. So pi is modulo a change of coordinate, the input Krylov projection. However, the big advantage that I have if I use this characterization, which is somewhat coordinate-free with respect to the Krylov one, which is related to coordinates, is that in the Krylov projection case, I have to use weird objects from a nonlinear perspective, which are these A minus 1, for example. I mean, I can still relate to this, but it's already somewhat borderline. Whereas if I want to do the output Krylov projection, then I have to go to transposes and so on. Whereas in this particular case, it's just a matter of performing interconnection, computing the steady state response, assuming that this response exists, and then you will see that through the Sylvester equation, which is something that we can easily relate for nonlinear system, we can actually construct the moment of the system without performing any operation which is different from a time differentiation and the change of coordinate, which is something that we can do very easily for nonlinear system. Okay, so it is important to understand that I now have all ingredients in place in order to be able to move from linear system to nonlinear system. I know that I need to do a projection, and I know that I need to construct this projection a la Krylov, so using the ideas of Krylov, but this projection cannot really be done with Krylov subspaces because I don't know exactly what they are. It has to be done through a Sylvester equation, which is associated to an interconnection between the system that I would like to reduce and the signal generator, which encodes the information on the particular moment that I would like to, that I would like to compute. For example, if my objective is not to compute G0, but is simply to compute G at some point S1, G at some point S2, and so on and so on. This is very easy because I can now construct S, for example, in this way. So if S1 bar is different from S2 bar, then L can be constructed as, for example, 1, 1. This is an observable pair. And then if you solve the Sylvester equation, you will construct through C pi's the value of the transfer function of the system evaluated at S1 bar and S2 bar. If you want to construct the value of the moment, not only the so-called zero-order moment, but also the higher derivative of the transfer function at some point, you just have to pick Jordan blocks. Right, pretty much like we have done here, that we selected a Jordan block of dimension 2 with eigenvalues at 0, because this is going to give you all the right eigenvalues and all the right objects that you need in order to construct this reduced order model. Okay, I wonder whether now is a good time to have a break, and then, like 10 minutes break. Hopefully, the nonlinear stuff is going to be even simpler than that, right? Because just the name of the equation is going to be different, but all the concepts are already here, right? So let's take 10, 15 minutes break, whatever it is, and then we'll resume with the nonlinear part.